Hello, and welcome to this Smith Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. And now I would like to introduce today's presenters and go over today's agenda. With us today, we have Tim Wooden and Stephen Davis. So today's goals are going to be to provide an integrated test solution to meet the required device specification so the product's fully functionality can be tested, and to ensure an out-of-the-box solution for high-yield production testing to meet time-to-market pressures. To read more about either of our presenters today, you can go ahead and look at that speaker bio window right next to the main presentation window. And with that, gentlemen, I'll pass things along to you to get this webinar started.
Thanks, Katie. Good to be here today. Stephen Davis, how you doing this morning?
Hello, everyone. Hi, Tim. I'm happy to be here, and thanks, everyone, for tuning in.
So Katie did mention that if you wanted to read more about Steve or I, then you could research us online. Please don't do that with me. You might find things you don't like. But let me get to the point of today's webinar. So today in our industry, and we are super excited to have you here, that's something that comes up in everything that we do and what we are looking to bring solutions to market for really relate to the cost of test. And the cost of test is a complicated formula that's not black or white, and the bar moves quite a bit as products, the evolution of products move on and performance requirements increase. But the cost of test is paramount to ensure compliance with industrial quality standards and specifications. This is super vital for semiconductor testing. Excuse me. Cost of test helps with ensure that out-of-the-box solutions can significantly reduce cost overruns, poor production yields, as the integrated circuits continue down the stream of the manufacturing process. The cost of test process is associated to the performance requirement of the product as next generation products come to market. They typically end up being a bit more than legacy products. And of course, the key to this is the qualification process that goes into deciding which product we are going to provide for your associated project. Just a bit of an overview. This is the semiconductor market and in segments that we participate in. Excuse me. So, the basis of this webinar was that we have our customers, and our customers are really looking to push the bounds of technology and bring cutting-edge technology to market. And the drive to provide consumers instant access to the World Wide Web has led our manufacturers to develop products that give customers near instant access to the digital world. To achieve this, mobile devices such as cell phones, tablets, vehicle infotainment systems have the most sophisticated system on chips ever produced. In fact, these SoCs must combine GPU, CPU, AI engines, camera processors, memories, 5G modem. The new devices are sending and receiving the largest amount of data with the lowest latency over the air, whether via a mobile infrastructure or a Wi-Fi connection to a wireless router. In fact, today's world runs on computer chips. The products mentioned above, to the fridge in your kitchen, the coffee maker on your counter, up to the most advanced missile systems for military applications. Nearly every part of today's digital society relies on nanoscale ecosystem of transistors working in synchronous harmony to achieve specific outcomes. And this leads us in to the challenges that manufacturers face to ensure once the integrated circuit is soldered to the final assembly, that the product performs as designed. We will highlight manufacturing process and challenges faced at various points in the intricate manufacturing process. We'll provide an overview of the solutions available today and our path to ensure that we continue to have solutions available to test in full functionality your next generation integrated circuits.
As a total solution provider, we work very closely with industry leaders in all the semiconductor segments. These performance drivers you see here are based on either a current solution offering or a roadmap product to meet a future requirement.
So, Steve, the products that or the requirements we have outlined here, are these industry standards or are these customer requirements that were given to the apps team? How did we decide totally on these?
Actually, the requirements we have outlined for this webinar are from both those sources.
So before I move on to the next slide, I just wanted to use this slide also to highlight a few important points that we are seeing as challenges moving forward. We used to just be responsible for chip level tests or providing solutions to test ICs themselves. We are now being asked to provide a socket or a solution for chip level test. Then after it's assembled to a module, that module then needs to be tested as these modules are now being installed into a cabinet where either 4 to 32 of these modules can run in parallel to create what we're seeing as the world's largest and most advanced supercomputers. Some of the next generation requirements that we're seeing are digital data rates up to 200 gigabits per second, single-ended PAM4 performance with signaling bandwidth of 12 to 14 gigahertz, DDR5, GDDR7, GDDR6W, digital and analog applications running at 77 gigahertz NRZ. A big one is multiple impedance signaling in the same device or the same pin array. We're seeing increased CPU core counts, and this puts a huge strain on the memory signal dependency. And of course, there's the thermal design power, which we're seeing anywhere from 850 to 1400 watts. And again, this is an internal document that we use for monitoring market, what the market's doing, what our end customers are looking for, what we see on the horizon, and making sure that we can check the boxes to that when a customer comes to us, we have the solution available to meet the requirement. And Steve will go into our process in qualifying a socket a little bit later in the presentation. The pursuit of higher compute density, chip makers are juicing their chips with more and more power. This could spell trouble for many legacy socket applications ill-equipped to handle new higher wattage chips. It was even announced recently the top server process manufacturers' most recent products announced late last year, and Silicon even released earlier this month, are the industry's most powerful and power-hungry chips to date, running at 400 watts and 350 watts respectively, at least at the upper end of the stack. The higher TDP arrives in lockstep with higher core counts and clock speeds than previous CPU cores from either vendor. It's now possible to cram 192 x86 cores into your typical 2U dual socket system, something that just 5 years ago would have required at least 3 nodes to achieve. And this is where it's kind of a catch-22, as more cores are often thought to be the answer. But the issue we run into, as do the OEMs, I believe, is the limit of memory available for the additional cores. In today's designs, CXL protocols are now being used to make up for the limited memory resources available, while allowing for adding other accelerators to the system with very little loss. And this is truly where our job has become harder, and harder is probably not the right word, more challenging, as we are focused on increasing critical memory bandwidth throughout the interconnect with enough margin to drive the signal that the memory value each core expects to receive. If we have too much loss or the system does not see the proper value to execute the task, then the test will fail and our solution will be. To add some more context around the challenges we face today, we'll move on to the next slide here. I've outlined what we're calling today's test methodology versus next generation test methodology, which includes the CXL protocol being embedded into the test program or the test process. As you can see here, in the traditional test methodology or today test methodology, we have a CPU device or server chip that would have a CPU core, the HBM, which is assembled on the substrate of the device. It runs through a test socket to a system board. That system board uses DDR4, DDR3 memory, which is socketed somewhere on the system board. But from a memory perspective, it is not running the high-speed memory signals through the socket interface, so you can get away with a little bit less of socket performance, not requiring a coax socket. The arrangement provides a lower latency and greater bandwidth connection than DRAM, as the HBM has a faster connection to the CPU than in a socketed base scheme. However, on the right of that, you see a GPU device that does not utilize HBM, as it's cost prohibitive and limited in size. For consumer applications like gaming or peripheral computing, the value or the cost associated to HBM just is not justified. In the test platform, a coax socket is absolutely required to test product, and this is just due to the GDDR memory being soldered to the system board and the GPU needing to communicate to that GDDR through the socket interconnect. So this coaxial socket takes into account these really, really high-speed signals that we can have very little loss in. As we move on to next-gen CXL protocol testing, as you can see, it complicates it a bit more, as not only are the server chips still utilizing HBM, but with the introduction of DDR5 memory socketed to the system board, DDR5 has doubled the data rate from DDR4. So the memory needs to be addressed more appropriately or closer to the GPU system. But the CXL protocol is now looking to replace PCIe Gen 5 where we'd only have to allocate 64 lines for that previously. You can with CXL, you can now run multiple GPUs in parallel. You can add more memory and even 3D crosspoint super high speed memory. So this definitely presents a bit more challenge for us on the socket side as we go through this process. Next, I really want to hone in and highlight high performance computing applications with a glimpse of the thermal challenges to come for our mainstream parts. One of the bigger challenges being substantially lower case temperatures compared to previous generations. These have fallen from 92C to 80C just a few years ago, and as low as 55C for a growing number of applications today. And this is a key problem in that removing greater volumes of lower temperature heat is super thermodynamically challenging. As liquid cooling has gained considerable traction, chips have grown ever hotter. During the Interconnect conference last year, we did take a deeper dive at various technologies available to cool emerging ICs. But while these technologies have matured in recent years, the efforts and research to meet these challenges has been underway for many, many years. One note you might see here on the slide also is we will be announcing the evolution of our next level thermal management system, and we will be announcing that in March 2023. So look for that announcement. We made some significant gains in this area. As we move on to the products that we have available to meet the challenges we discussed, we're going to allow some video pleasure here. So I hope you enjoyed that video as much as I did. That music is like a cup of coffee for me. So, but while we're here today, I'm going to pass the microphone to Mr. Stephen Davis to give us a little background on the products we have available and how we select those products.
All right, thanks, Tim. Well, in the next slides, we will go through the process that applications engineers take to ensure that when the socket's delivered, it works out of the box. To start is our flagship product, known in the market as the DaVinci product line. This is our patented matched impedance coaxial technology. Now, this slide, it lists several advantages of this technology, but the main key here is the proprietary insulated metal socket body. This allows for the entire path, the entire signal path, to be shielded by a grounded body, which emulates a coaxial structure at the critical signal path for high-speed performance. Additional benefits of this is high structural rigidity. We see very low deflection rates on large pin count sockets, And then the thermal transfer away from the probe array is superior to a plastic socket. But we can utilize, single-ended spring probe design for extended compliance, low contact resistance, good current carrying capacity, and ease of socket probe maintenance, as in a standard vertical spring probe socket. So DaVinci is well adapted for the high volume manufacturing environment.
So, Steve, I know we're listing DaVinci technology here, but as an apps engineer and you out in the market, this is a majority of the technologies that we're using for these advanced applications. Is that correct?
I'm sorry, I missed that.
So just the DaVinci product itself, we're talking about advanced technologies and the server applications. A majority of those applications are going to fall under this product line?
Yes, due to the, challenging signal paths, the pin maps may not be all that friendly for a standard socket. So to get high speed with low crosstalk, we need the coaxial structure.
Great.
So the exploded view here, this kind of illustrates how we can still utilize a fairly traditional socket body construction. We have either a fixed frame or a floating platform for device alignment. The socket frame and the probe cartridge is in the insulated metal material, and this houses the DaVinci probe pairs. We have the signal probe that's tuned to match the target impedance, and then we have the high current low impedance probe for handling power and ground.
Hey, one more. Let me just get back. Let me go one more question back to you, Steve. Can you just briefly help us understand? We hear that in the market there's already solutions available for 112 gigabits or 90 gigahertz test socket solutions available on the market. And, I know we know that although this is not inaccurate information, can you just add a bit of clarity as to why it's a bit taboo to say there's a one overall solution to meet every one of those requirements?
Yeah, correct. We have sockets in the field that are testing these speeds and data rates, but what really kind of defines the ability to achieve the speeds are the customer device pin maps. We can shield and provide the best signal through the socket, but every customer device is unique. There are several factors that, contribute to the end performance.
So
this gets us back to our process.
Truly not making it. We don't really have a one-stop fits all, right? I mean, everything we do is a case-by-case basis. They're gonna go into that.
The DaVinci product line is tuned to the specific requirement.
Awesome. I think one thing that we just need to highlight, the DaVinci technology is considered the gold standard for high-performance test applications. And we do, in our patented technology, we have a portfolio of spring probe options, which means that we really can tailor the solution to meet the requirement, right?
Yeah. Each we have a few probes in the portfolio at each product, and they're tuned to different impedance targets. And even as such, we can still have a little bit of leeway in tuning for the best performance, depending on how challenging the pin map is for the device with the cavity and the structure. That it really helps to kind of achieve the best RF performance.
I know I kind of jumped the gun. I pushed you out of how we practiced. I'm sorry about that, man.
Yeah, this gets us back to our process, which starts with the customer input. The expected RF performance, power of the device, the customer mechanical package drawing, and the device pin map, which really defines the high-speed signals. With this, data, we will take the high-speed signal area of the map and we'll run an RF simulation to evaluate the performance of the selected spring probe in the customer configuration. This comprehensive simulation provides expected insertion loss, return loss, TDR, near-end crosstalk, far-end crosstalk. These slides here show examples of what you would see in a simulation report. We run the simulations out to the target frequency's third harmonic if possible to check the behavior at these points of interest. You can see here we've got a particular pin map for differential pairs in this case, and we've got a couple of target base frequencies, and we can see out to the third harmonic at 80 gigahertz in this case. If the simulation meets the requirements with proper margin, we'll share the results with the customer and move on to the mechanical design.
And if it doesn't meet the customer requirement, we do this for every socket we're qualifying, correct?
Yes. If we have like a challenging insertion loss, return loss target we need to meet, and at a particular frequency we're seeing some spikes or something, then we can actually tweak the cavity structure a little bit to kind of smooth out the response and get the best possible signal path.
So as an apps engineer, you submit this information, and if you were to come back and the SI team were to come back to you and say, hey, this pin map was not able to be achieved with the offer or the selections that you had made, what would you do?
Well, we go back to engineering and develop for the app, for the requirements of the industry.
So you have a different probe configuration, or would you design a new pin? What would you do in that?
Well, if we don't have the pin available at the moment, like I said, we have a few. We would start with the one that would best target that impedance target to get the smoothest, signal through with best return loss, insertion loss.
So you're saying you have an arsenal. You have an arsenal of weapons that you can use.
We have a few. We target different. We can try a different impedance. It depends on the pitch also. Which product we will choose to start with the simulation. Generally, the ARP engineers have a pretty good idea of the best arrow in the quiver, to target whatever the requirements are.
Yeah, I wouldn't want to have your job. Sorry, Steve. Thank you.
So assuming we can meet the electrical targets during the mechanical design phase, we'll run FEA, and we'll ensure that the socket strength meets the deflection requirements. And we can make any changes if necessary. The mechanical designer can, shore up the body design. We've got some challenging, PCB mounting due to, high, trace routing out. Sometimes we're kind of limited on mounting screws, but we've done some pretty large devices, and so far the insulated metal body has proven to be very robust, and we see no issues with deflection. Also at this point, during socket design, we'll start the thermal analysis and do a simulation on that and ensure that our manual test lid heatsink meets the target thermal design power. And then I think we got a good product at that point. We're ready to manufacture and deliver.
Yeah, thanks, Steve. Super, super helpful. As we go over more of the products that we have available to the market, not only, we really highlighted the DaVinci product in this segment, but at Smith Interconnect, we really have a wide available options to meet many different test requirements. And it starts with our area array test products. And this includes the DaVinci socket, but it also includes our standard array product line. And this is really focused in on GPU tests, CPU tests, the AI, deep learning, high-speed memory, analog RF. We have our Euclid product line, which in the industry is typically referred to as POP, or package-on-package test. And this is for really tailored towards the smartphone CPU market, the wearable technologies, NFC, consumer and industrial applications. Our peripheral package test products, which are scrub products, and those are more focused towards the QFP devices, where high current is required for automotive segments, industrial, wireless communications, and finally is our wafer level test product. This is our Volta product line. We can test down to 180 micron pitch with a vertical spring probe. This can be up to 32 sites, and we're really starting to see more and more applications in this product line, and I hope that we have a future webinar around the Volta product line. And to summarize, our DaVinci series products, as I just mentioned, the semiconductor market, current and future challenges, it really boils down to the insatiable demand for data, the need to access data everywhere and anytime. I think if you're in this industry, this is absolutely something that we as a collective are looking forward to achieving together. Our motto is cutting edge connectivity, and we look forward to bringing cutting edge connectivity to our customers. So this slide will be passed out at the end of the presentation. I believe you'll be able to download the webinar, and you'll have access to all this content. Of course, you won't get the funny jokes. You won't get Steve and I, the great humor. But we greatly appreciate the time you've taken to sit with us today. And we look forward to talking with you in person about your project or product. And thank you again for the time today. It means a lot.
Thanks, everyone.
All right, guys, thank you so much for a great presentation. So we are going to move into some questions from our attendees in just a moment. All right, gentlemen, so our first question here, this is from one of our attendees. He is asking, so it's kind of more of a statement, but time of RF simulation, general characterization or specific application pinout?
So I think the question is a loaded question. Steve, I'm just going to take this one real quick. I think the time domain of the RF simulation is a question that we would ask the customer. So if there is a specific TDR that we're targeting, our impedance will set the impedance, and the simulation output will generate the TDR. For simulation, we are doing application-specific pinout, as we've part of our NPI process in bringing a product to market. We characterize each one of our products and test to failure as part of the NPI program. So that information will be available. We have the way we've characterized it to correlation data, and then we'll run customer-specific patterns based on the values that we've collected.
Okay, great. Thank you so much for that answer. So our next question here, what is the largest package size that you have designed a Da Vinci socket for?
I saw a pretty big one recently. We have one out in test, in a test, production test environment now that is 90 by 90 millimeter. Can't remember the exact pin count, but it was a pretty big VGA device. And large socket, we had, I think, six mounting screws positions available, and we were okay on the deflection. We didn't have any deflection issues. One thing that we do have in the Da Vinci portfolio is we've got a couple of different pin lengths, and even the longer pin, due to the fact that we can shield the complete signal path and tune the cavity, we still get really good performance even with the longer signal path, and that allows for longer stroke and a more rigid socket. So, we're okay up to 90 so far, and I think larger are on their way.
Okay, thank you so much for that answer. Next one here. Can you build a single socket that tests a GPU, CPU, and with memory devices on the peripheral instead of the memory soldered to the PCB?
So you want me to take this one, Steve, or you got it? Rock, paper, scissors?
Go ahead.
I got it. Yeah, so I think the question is, can we build a socket with multiple sites to test one product, being, say, a GPU in the center of the socket with memory devices around the edge, and this is just me being familiar with the GPU application, so I think that it's probably tailored towards that question. But the answer is yes. We can build a socket where it can touch a full, in this case, system board, where it would have the GPU in the middle, and then it would have the corresponding memory locations on the outside of the socket, where that you can test anywhere from 8 to 12 memory in tandem with your GPU test, or be able to change memory manufacturers without having to change the system board or different memory speeds. So yes, I guess I get it. Just said yes.
Now I get it. I have seen that where we have multiple sockets in the socket and individual plungers to test.
All right, gentlemen, thank you both so much for that answer. All right, we've got time for a couple more here. So if any attendees have any questions, feel free to ask them now. If we don't get to that question, we will reach out to you following today's webinar. So next one, is it possible to make a coaxial socket for a 0.30 millimeter pitch?
All right, sorry, Steve, I'm just going to jump in on this one also. Currently, we don't have 300 micron pitch available in the coaxial structure. It's something that's on our roadmap. We're actively developing a solution to meet this requirement, and we're really trying to understand which one of our customers are going there. We've had a couple requests, but it's not been a huge ask as of yet. I don't think that packages are quite there, but it's something that is in development.
All right, great. Thank you so much. So we've got time for about one more question today before we're going to wrap up. So if we didn't get to your question, do not worry. We will get back to you. And then just a reminder to grab those resources before we end the webinar today. And we will also have a survey that pops on your screen, so feel free to fill that out since your feedback is always important to us. So, gentlemen, the last question for today: is the coaxial socket better than elastomer socket for the test based on your expertise? Do you provide Da Vinci elastomer sockets?
I'm going to let Steve.
We don't
answer this one.
We don't have Da Vinci elastomer sockets. I think the vertical probe solution is a better solution. It's better suited for high volume tests or lots of test cycles, and certainly for larger packages. And we're seeing so many large GPU, CPU packages that we generally focus on the vertical probe Da Vinci coax solution as opposed to an elastomeric. So
all right,
my answer is vertical probe's better. I'm going to go right ahead and just put it out there. It's better.
I was going to try and mute you before you. Sorry, I know Steve's love for the elastomerics.
All right, guys. Thank you so much.
Yeah.
So that's the last question for right now. As I mentioned, we will get back to anybody that asked a question and we didn't have time for. So I just want to say a huge thank you to Steve and Tim for a great presentation today. Thank you both for being here with us.
I enjoyed it.
Thank you, Katie. And again, everybody that is here and was able to make time to attend. Thank you so much. We look forward to working with you.
All right, awesome. Thank you guys so much for being here. And a huge thank you to our audience members as always. Take care, and we will speak with all of you soon.